laser beam welding. So it's kind of a cool thing. Now that we are on the subject, we'll bring in a few more concepts related to making beams. A lot of time the beams are rolled. So we talked about our billet last time. And essentially, one way you can tell that it's being rolled is the final geometry a lot of times is got big radius, just like this, and it's rounded. So you have to go through a sequence of rolling to gradually make that shape. So this would be an S-type beam where the flange here gets a little thicker when you go towards the center. So from here to here, a bunch of rolling processes, it's high temperature, and you do it a little bit at a time. If you try to improve here, you can manage, when they call it a W beam, it becomes pretty flat on the lower flange, and then you have a little bit of a radius here. So you're still able to identify it as essentially a rolled product, but it can be more complicated. So one of the aspects here helping to identify was welding, there's a little bit of roughness. And the other aspect, instead of having a nice fillet, it actually looks the other way, like this, because we had a welded bead. Most likely we had a prep done to this piece. So say it was a double V prep like this. And then when you welded, you had your two fusion zones. So a weld from each side and making it completely solid. Now, if you have some anomalies in this weld at the root, it's fine because you're in the center. You're not in the area of high stresses. So these joints will be good for, ultimate strength. In fatigue, they may very well fail here because there's a little bit of a stress concentration at the toe. So it's not the best design. This is more robust, but it is done in even mostly building construction. If you are in another country, we had a project in Pakistan where they had essentially a machine they would use stock, so very flat pieces, and cut them up to make beams of different height, different length, all on site. That's not to say that they didn't have any problem, because if you're going to do this, a typical a beam in a building may look just exactly like this. It's pretty thick wall. You're looking at about an inch or 2.5 centimeter of wall thickness. So when you try to put a weld here, the weld, when it cools down, it's going to shrink a lot and cause deformation. So you can have a lot of distortion in what you're trying to manufacture here. We'll go through more details on the welding. That's part of this fall. But I brought this one in because you can do it in at least 2 or 3 different ways. The idea of the extrusion, again, is you need a lot of flow stresses to try to get through this. And then you're stuck with a certain geometry. So one, again, big advantage of doing anything welded is if I say, oh, I'd like 2 inches more in depth of my beam, no problem. I'll just get another plate and weld it again. So there's a lot of advantages of using stocks to make assemblies. All right, let's go over where we left it up. So on Friday, I was describing to you what happens in rolling or in deformation at temperature. If you do it at relatively low temperature, say ambient temperature, and we get these grains that are very, very stretched and deformed, what you see here is what happens as you start eating up that microstructure. So we have a cold work structure on this graph, and as we go in temperature, we're going to go through recrystallization. So I drew it for you. It's essentially in grains of a lot of deformation. You have little zones that nucleate, and they have very small dislocation density. Now, ideally, you want this to happen exactly like the schematic we have, where all these grains convert and develop very, very fine grains within them. But the example I circulated where we could feel the roughness of the tensile duct bone, that was a case where some grains grew much bigger than the others. So anomalous grain growth can happen if you're heating too fast or you're heating too slowly. So there is essentially an ideal range of temperature and deformation rate where all the deformed grain turns into new, smaller grains. And if you keep eating up, then these grains starts growing. So it's just the general concept. I don't want to go back to it in too much details, except to think that at high temperature, it's easy to see that regardless of the exact material, you can reach that steady state where you're going to have pretty much the same microstructure as you move forward. And that's what happens on these curves here on stress to deform over the strain applied during a rolling operation. If you're at a certain temperature, you get to this level where there's always some grains that are being deformed, but there are others that are essentially recrystallizing. There's some that are growing, and it's just staying the way it is. We use that a lot when you see these the videos I was showing with the when the steel is red. Essentially, that's what we're doing. Wanted to essentially capitalize on what we've learned so far and go back to the example of the technology that I discussed in my first lecture. It's a tool that we're working on. So what you're looking at here is very fine hardness testing. So we made indents on a polished section of a pipe. So the pipe is going this way, and we're looking at a cross section. So let's see. Here's the pipe. It's got a certain wall thickness, and the axis here is from 0 to 0.25. That's what we're looking at. So we see that the hardness is higher on the surface. It goes to a minimum in the center, and it goes higher on the other side. So if we don't know anything about what happened, we can essentially hypothesize, say, hey, because it's harder here, as I form, I essentially bend the plate because this pipe came from a flat originally. It just essentially rolled and then seam welded here. So I have my weld in this area. And so right now we're not looking at the weld area, but we can see that as if when I'm forming this, I'm going to be stretching the material on the surface and compressing the material on the inside. Now, it turns out, according to this, that the effect is about symmetrical. So we're bending around the neutral axis. So it's a nice theory. So what we did recently is we tested it using finite element analysis. So we had this product here. We did a tensile test on it. So we're getting our stress strain curve to break point. We used the part of the data that is before the necking, and that's what we input into this shape, deform it using laws of physics, of plasticity for metals, and here's what we got. So we got essentially the center core, only about 1/5 of the thickness that remain only in the elastic region. So when you see blue, means that you're below the yield point. And then everything above is above the yield point. If we go to our strain level here, 2.2%. So we only went about this far. So can that explain the hardness profiles? The answer is yes, because even if you only have 2.2% strain, essentially the stress strain curve of the material goes from about 46 KSI here all to the way a little bit above 60 KSI on the surface. Now, it turns out that we did run our test on the surface, and we were getting about 59. But it's a prototype; it's not exact. And what happened is we had to assume we didn't believe our tool was wrong, so we just said, yeah, there's got to be a reason for this, and we started investigating backward into what was going on. So we run the hardness. We also looked at the microstructure of that specific pipe. It looks exactly the same. So we'll go through heat treatment in the next lecture. We're going to start that on Thursday, but you see a little bit of the black zone, that's the perlite, and some of the white zone is essentially the pure iron. If you look at that microstructure on the surface as opposed to mid-wall, it's just about the same. So the fact that we were getting different properties cannot really be explained by a change in microstructure. Now, I think you guys realize when we do the cold deformation, we're changing the dislocation density, but we're not changing how it looks under the microscope because the dislocation is so small, you can't see it. So all of this makes sense that if we start with the flat, we get our cold working on the surface, nothing else happened, and we can essentially, the good news for us is we can translate you a surface measurement into a mid-wall measurement just by using our final analysis, just as a parametric study. We won't do it every single time. We just arrive to a correlation equation and apply it. Now, in other industries, so this is an oil and gas pipeline material. This is a ASTM, kind of ASME for a boiler and pressure vessel pipe, so a more expensive piece of equipment. Here they did a heat treatment. So I think you can, I wish I'd magnify it. I mean, we have a lot of these images, but roughly speaking, I think we'll agree that there's a finer structure on the surface than what we have in the mid-wall. Anybody wants to explain that to me? Because we had to do it. I don't know anything more than you do by now. Yes?
So when you're trying to quench it, doesn't it take time for the temperature to drop to the middle of the wall?
Yes. It wasn't quenched. No. So it started as, the plate here started very homogeneous. I mean, otherwise, yes, that would be one reason for having variation. In this case, it started on a flat, they bent it, and then we went through the documentation and they did an annealing procedure, just like the graph I showed you at the beginning. So it wasn't enough to change the face. It was just enough to do this type of thing. So the center, if we magnify in on that pipe, we see the elongated grains, and they're bigger. On the surface, we see smaller grains that are almost equiax. So essentially, the surface of that pipe recrystallized, but not the core, because it didn't have as much internal energy in the grains. Overall, it means it's a lot more difficult to take a surface measurement than go to the core. Because now you don't have just a strain, you have a different microstructure to deal with that's going to have a different hardening behavior and a lot of other characteristics. So these are different stress strain curves. The other case we had was really the same stress strain curve. So it was, we didn't know at all what we were going into, but when we realized it, we said, well, it's a good thing we, of course, 3 people, or at least took that class. Yes?
Is there going to be a lot of residual stresses?
That's a very good question. The residual stresses on this pipe will depend on exactly how you clamp it. If you clamp it and when you weld, you continue pushing, because you have your seam weld here, there's going to be essentially, if you let it loose here, it's going to be opening up a little bit. So you start from flat. If you didn't have the weld, you'll have a spring back, right? So let's just draw it. I'm trying to get it as close as I can together, the two halves. If I did not have the weld, what's going to happen here is it's going to spring back on me and leave me a little opening. Is that what you were thinking?
As you said, like when you go from the surface to the middle.
Yep.
In the middle is like it's in the elastic region.
Yes.
So that's gonna change, right? Because the plastic region, they will not go back to the original.
Yeah. Okay. So I think so. Okay. Maybe I was misunderstanding. So you're talking about a built-in stress in the product that may also influence the microstructure change. It's not as big of a factor for the microstructure. So if what you're describing is if I stay very long at temperature in my annealing process, I can heal a lot of these residual stresses. We call it a stress relief treatment. So what happens there is anywhere that there was a lot of stresses between the surface and the core, because at temperature my yield strength goes down so much, I can just deform and get rid of a lot of the residual stresses. So that is something that would happen on the second pipe, the one that's got a different microstructure. Not only it has a different microstructure, if you cut it up, it's going to stay where it was. The pipe that was cold worked and welded, if you cut it up, it's going to open up on you a little bit. And part of that is because of that stress gradient. So what you're going after is there's a little bit of a tension compression zone in the center. And those are really there and true. But typically, it's not taking into account in steel design. And the reason is, say I have a little bit of a tension here on the surface. I'm almost close to yielding on the surface, which happens if you have a weld, for example. So be it, I will deform. We are a lot of times relying on steel being very deformable and not creating a problem in terms of a fracture. So if we had a very brittle material, all these considerations about exactly what the stress, so if we're looking here at a stress level through the thickness, what it would be will matter. But because we're saying if one spot here reaches yield, that's fine, because the overall behavior of the wall is going to remain elastic or approximately elastic, and therefore I don't grow the diameter of the pipe. So people are more concerned about growing the diameter than having one zone reaching some plasticity. It's a good question. Gets me a little bit deeper than I thought. But so the stress relieving, by the way, is done on forgings. It's even done if you machine in aerospace. A lot of times they'll machine down a piece of aluminum and they'll do a stress relief before they do the very final machining, just to get rid of all the deformation before the last step. On large parts, it's very important because every piece of wrought product will have some of those gradient in stresses through the wall, especially if they were cold form. So if you're removing the surface, now all of a sudden it bends on you. It's just part of what it is. Okay, just going a little bit more into rolling. We talked that, and by the way, this is a reference that I posted on Stellar that goes through all kind of the main deformation processes for metals. So I invite you to scroll through it. I made a nice PDF of that one chapter. I think the book itself, I have the entire book. I think that you wouldn't go through it and be all excited, but that one chapter I think is probably worth a quick read. It talks about friction being very important in forming operation. In the case of rolling, we use it. We use the friction between the roll and the product to actually drive to drive the metal through. So there's been a lot of study done in terms of, first of all, making sure that you don't stick, so between the roll and the product, but also that in this process you maintain everything under a compression pressure as opposed to tension, and that is to avoid the problem of cracking during forming. So you want things to be in compression. It's not a problem with rolling. It can be a problem with other processes that we're going to see. This is just for you to bear in mind that both ways of forming are done. When you do it hot, the good thing is you can deform a lot more. You can change the aspect ratio of the part a lot more. You typically do it at a pretty high temperature that's a function of the melting point of the alloy and at high strain rates. When we talk about cold working, probably the most used cold working processes are for copper and aluminum, for electrical conductors. With those, you want a relatively pure metal, so you have the maximum conductivity, but you also need to be strong enough so when you hang the wires, they don't stretch. And it looks easy, but in reality, it's a limiting factor, especially for aluminum. If you have these big conductors between transmission towers, they sag and they do have a lot of tension in them. And therefore, you do want to cold work them for the reason here of increasing the yield. In manufactured product, if I want to buy plates to make an assembly that I won't machine, it's nice to buy a cold work product because it has more dimension accuracy. Now, if you're going to make changes, that's exact opposite, because you know that your cold work product is going to have this skin with a lot of tension or compression in it. There's going to be a very high difference through the thickness. Now, to avoid that, you can anneal your cold work product. So you maintain the dimension and you get rid of the residual stresses by stress relieving. So it comes to all about the same, but there's in a lot of very big industry, there are multiple ways to do this. I'm just trying to go with you quickly why we do it in such a way. So why would we use other processes? The deep drawing, probably most of you know that's how we make the aluminum cans for Coca-Cola and all that. So you start with a circular blank. And you essentially put it over a hole, and you hold the flanges here, and it deforms and draws the material and stretches it very heavily. So you're looking here at a deformation factor of more than 2 to 3. What a deep drawing operation requires is a lot of strain hardening, because otherwise you start tearing in one area. It's a little bit like you have necking, like you have in a tensile test, if you don't have a lot of strain hardening. So there's specific aluminum alloy designed to be very, very soft to begin with, and then as they harden, they allow you to deform. Now, there are certain cans that are not done all at once, and that is because you want to stop and soften the material again, and then continue with the same hardening process. The same happens a lot in forging. So forging here, I think I have one slide on forging, but if you take this square here, and I'm saying I want to flatten it because of friction against the surface, what happens to this when it becomes thinner? So let's say I'm moving the upper die here. So it's thinner, it's wider, but it also, because of the free surface, becomes a little bit rounded at each end. And you can start having tension in those areas. So it's a very practical reason why on a forging operation you tend to do it multiple times, because you need to avoid that tension zone. I have a forging here, and the reason you can tell it's a forging, there's a little bit of a lip on the back side here, so that you wouldn't have in a casting or a machining operation. The example I'm circulating is essentially an adapter for a pressure vessel. So if I have a big tank, a lot of times I need pipes to come in and out of it. Now, I can do this multiple ways. I can just bring the pipe and weld around it. So that would be a joint. Let's say we have a pipe wall. We poke a hole in it. We have the pipe coming in, and we put a weld. That's an option. What this design allows here with the forging is I have the same hole, and I have my forging on top of it here, so it looks like this. Then I have the tread. So one main advantage is I can put the pipe later in the field without needing welding. But also, my welded is further from the pipe itself. So it's got a much better moment capacity. It's the biggest stress riser here is between the forging and the threaded end, as opposed to being right in the weld. So this is going to give you a better long-term strength if you have vibration than if you try to connect it directly. And to avoid having breaks at the threads here, and that's why we use a forging. We don't want to use a casting or anything like that. And we don't want to weld here. So I've seen on big engines for ships, people come and do repair. Well, this is loose, so I'm just going to weld it. And then it fails because the threaded connection here works in shear, but when you put a weld now, the weld is acting transverse in tension and cause fatigue failures. So I've seen that a lot. So that's points. There's always a reason for doing it different ways. Yes? It's just because it doesn't have this very fine microstructure that's more resistant in terms of cracking resistance. It has all the segregation, it has the dendrites, and all these features that essentially make it more prone to crack initiation in cyclic loading. So I think extrusion, we all understand it. You need a very good tool that can resist the wearing from all the material coming through it. That's because it's always the same material. On the roll, you have material all around. You have more options for cooling. Here you need strength. So the idea that you'll put a cooling element in your extrusion device is more complicated. You can, but typically it's a little bit further back. So it's very well suited for plastic and aluminum. It's a lot more difficult to do with steel. What is there? Stretch forming. The main example I have of stretch forming is the aluminum fuselage. And because we already discussed residual stresses through the wall, this is a good way to go here because that's an advantage. If you essentially take the sheet of aluminum for the fuselage and you pull on it in tension all at once and essentially have it adapt to the shape here that you're looking for, so you have a form shape and you stretch over it, the really big advantage here is when you let go your tension, it doesn't go into all sorts of different shapes. It's very different than our pipe example. With our pipe here, we were putting forces this way, so we knew that we were in tension here and compression there, so as soon as we let it go, it's going to go the other way. So this example allows you to have tension everywhere, and that's why they do it. They don't want, they need a very high dimensional accuracy, but also they are in an industry that is trying to avoid high residual stresses for service. The forging, we already went through. The main aspect here is you have these free surfaces, so a lot of times you end up with multiple operations. You can end up trying to push in different directions at the same time, and that's also a very complex operation. These very, very high forces. So we're typically looking into very, very large components or very high volume, like steel wheels for cars. They are forged, but it's because somebody decided to go through the process of making it like a 10-step operation that actually works. Because if you try to do it all at once, I'll say good luck. Tube forming, you can form a tube without having to take it from a flat and weld it. Now, it does, well, first thing, there's, we call these seamless pipes. But if we think of, so this is with a seam. If you think of seamless, it doesn't say seam free. Just the same way we have stainless steel as opposed to stain, not staining steel. So sometimes, and it's part of some of the codes that you can do the same process where you have a plate, you form it, you put a weld in it, but then you go to this drawing operation to essentially homogenize the weld so you can't see it anymore. And that is considered a seamless pipe, even though you did put a seam in it at some point. Now, some of the advantages of drawing, if you do it, especially if you do it with a mandrel, is you can decide what dimension you want to very precisely control. So this is a good way to fix the ID or the OD of the pipe very precisely. You have the option to do that here. And it's used a lot as a final step in precise pipe making. Not the oil and gas pipe that we talked about. Those still have the welded seam at the end, and they never went through anything as sophisticated as putting a mandrel through them. Yes? So there's a large range, and the question is really good because a lot of times if you're talking about a small pipe, it can be easier to put a mandrel through it and essentially poke a hole through a billet as the starting point, as opposed to welding it first and then drawing it. So it can go both ways. Typically, smaller means you poke it first and then you reduce it in size. But when it's really large, it's better to take it and do it the other way around. Yes.
So that would be actually seamless. I mean, the smaller one where you poke a hole.
Yes. So that would be a way where you never used welding at all. Yes. So you seam free. But it won't normally be distinguished in the material specification, which way you got to your pipe. If it's been drawn by a certain minimum amount that you don't see the seam, you can do it whichever way you prefer. So we talked a lot about metal forming, and I want to make a kind of a transition to plastics because I know a lot of you will have projects involving all sorts of composites. So let me just get rid of this. It's something we're going to start now. We're going to finish this on Thursday. The other thing I want to do Thursday is bring in some examples of failure analysis. We talked that I think it's a good way to bring some practicality into this. And maybe there's one thing before we forgot, because we spoke Friday about inclusions. And you guys had some good questions about the inclusions. One question that came out is, why the inclusions stay in the middle. Let me push this over. I can do that. Nope. All right. We talked about the inclusions that were the product of segregation. So we have the entire billet. We start forming our dendrite on the surface, and when we get to the center here is where we have more alloying elements and we have more impurities. One thing we discuss is as we go through a process of making this into a very tiny wire, these types of inclusions have no reason, they're not part of the material crystals, so they don't diffuse. They essentially are little piece of stone on the bottom of the river. They don't want to mix. They have no sense of gravity or anything like that, so they tend to stay in the middle. And that's why on small, very high-strength wire, you can have a failure that is not on the surface, that is in the center. because in the process of breaking down these big inclusions, they still remain in the center. One type of inclusions that I've not talked about are the surface ones. So here you have a particle that essentially came from the mold. It can come as a debris in a forging operation, and these are surface inclusions. Now, those tend to be a lot more trouble, especially we don't have, well, I mean, trucks still have leaf spring suspensions, not so much cars, but I worked for a while in a ruling facility where we were making the leaf springs for cars and trucks. And when we were getting a premature failure, a lot of times it's because we did have an inclusion that was very, very close to the surface. The leaf spring is essentially loading and bending, so you have an effect of the high stresses there. And then the exercise was to look at the chemistry and figuring out, does that come from our refractories that we use all the way up in the casting process, or does it come later in the rolling operation just as essentially a chips or something from the metal that just got rolled into the product. So those are rolled in inclusions. It's more and more controlled, but it still happens on pipe. And it is a site for fracture. So a lot of times it's one of the easiest things to rule out when you have the fracture surface and you find the origin, you try to see if there's a particle there. So that was kind of tying back to what we had last time. So plastics. Just the same way I started talking to you about casting, I said, castings, we use them for these ductile iron pipes, for water distribution. Well, the plastics now, we use them everywhere, right? A lot of times, they're not the most critical components. So this is a good example. The legs, they're steel, welded together. It's a nice welded tube. I don't think they've been really drawn. These are probably seam welded tubes because we don't mind, And then, actually this is a little surprising. I guess they assume that I won't rest on this for hours and hours, because if I did, it may deform eventually and become weak. So I think that it doesn't say on it, don't lay down the whole night, but it will deform it permanently. Pipes is a big application, and for smaller diameter natural gas lines, for the past 30 years or so, we've been using a lot of HDP, high density polyethylene, for a number of reasons. Cost, not only the material, but also the way to lay it down in the ground. It comes in big rolls, not this one, but much bigger roll. And then they have essentially a fusion welding process to put the different pieces together. But because of the ability to put it on a big core, you don't have as many joints to do in the field when you do the installation. So that's a big cost advantage. So we have some drainage pipe. We have a lot of under the hood components. So when we're thinking about this one, these are definitely extruded. The fittings tends to be just molded a lot of times. So when we think about fittings, you do need a bigger wall thickness on them, because you can't get as good of a property of the casting itself. So the same concept we discussed with metal applies here to those fittings. And the under the hood component, this is a case where you need to inject from a lot of different locations and worry about where they will merge together. So again, the biggest concern really with using a plastic is that if it's for a sustained load, a load that you put on and it stays there, that it will deform over time. And the deformation, we're looking at polyethylene here. happens on a logarithmic scale. So you get a little bit at the beginning. So say here, this is after a day. So after a day at a given load here, what do we have? 5 megapascal, we got 3% strain. So that may be kind of applicable to something like this here. And that's fine. I can do that, get a viscoelastic strain. So the problem is if I keep going and I'm looking at a pipeline that needs to be designed, say, a 50-year life, is eventually I can literally break in a very sudden way. So there are two things that happen as the plastic deforms. One, it becomes longer. That's just the flow. But there's also these microvoids that will form into it and can lead to these more brittle fractures. So the brittle fracture happened here at a lower stress level. And when you were at a higher stress level, the green curve, so 10 plus megapascal, you just become, you're soft enough that you keep deforming and deforming and deforming and deforming. So this is, you're almost forming it into something else without breaking it. So it makes it for, because you have these two different behavior, we won't go into the details of that when people talk about time temperature equivalence. There is something to be said with the polymer that if you give it more time to deform, that may be the equivalent of more stress. That's a little bit what the principle says. But that is so long as your acceleration factor by putting more stress doesn't change your failure mode. And in this case, it does. So the consequence of this is if I want to put a polyethylene pipe in service, the minimum qualification test, if I make some very, very small changes, I already know very much what the material is, I make just a small change, I need to go to 10,000 hours on my test. So it's about 4 months, and it puts us, right here. That's almost, I didn't make it that way, but it works with this curve that you essentially are accelerating. It's not 50 years, but it's long enough that you are generating the failure mode that's the problem one. Just getting the pipe a little bigger, not a big problem. But if you do start forming small cracks in it, that leads to a catastrophic failure. So there is an option of accelerating the test, but it has a lot of consequences. What it means a lot of time with a plastic is you either assume it's going to be very low load. So for under the hood component, like the protector for the car cooling system or anything like that, you say, okay, it should stay in place. If it sags, well, maybe it rests against something else and that won't be too bad. So there's a lot of kind of protective measures, so it's not as consequential if it fails. Like this chair, if I do leave it in my office and I come back and there's a big V shape in it, then I won't use it. It's pretty obvious, right? But if it's underground and it was under pressure, I'm hoping that it only grew a little bit as opposed to developing these small cracks. So there's a. I was talking a little bit about the advantage. It's less expensive, and then we didn't talk about, but yeah, I mean, it doesn't really corrode in a common sense. It does have its own issues with the environment in terms of cracking resistance, but it has a lot of advantages. But then there's this component that we never have to worry about steel that now we do. It's how it's going to change over time at ambient temperature. Now, why does it do this? And this is going to lead us to talk about forming next time. The polymers have this supramolecular structure, very, very long chains. And you're all familiar with essentially getting, if I pull on it, let's do that here. So if I have a constant force over time, I'm looking at the deformation. So I just put a dead weight, so I get a certain elastic response at first as I'm loading. So here I reach my sigma. And then it keeps deforming and deforming and deforming. Now, if I'm looking at it on a linear plot, I may think, well, nothing's happening anymore. But when you plot this on a log scale is where you still see that it will be going up in deformation. So what exactly is happening in the material? You can differentiate it in three main ways, and that's what at least helped me. We'll see if it helps you. One is just really an elastic deformation, just movement of the macromolecule. You never change the bond-to-bond distance in this case here, because the carbon-to-carbon bonds, they're just so strong, they don't change. So the first thing is you kind of move them, and you essentially moving the van der Waal forces between the different chains. That's how you get your elastic constant. The second step here, what I call the viscoelastic, is now the chain wants to move a little bit more, and you have these side groups. So you have the carbon-carbon chain, and you have side groups. They start rotating, and that takes time. It takes time to rotate and allow for some movement. And that's the viscoelastic part of it, because you can revert it. You know, I went past an obstacle, so I move my side group. If the load comes back, I can do the other way around. Nothing has really changed. The last step, which is really a viscoplastic process, is now the chain really starts to move completely on its own. It starts to flow in relative to the other chains. And that's a part of history of deformation that typically does not get recovered. They all happen at once. But at first, you see this one. That's the pretty obvious. Then you start seeing this, and when you're done doing these small movements is where you start really having the chain displacement. So you'll see exactly how it comes in when we talked a little bit more in detail about the creep. Just to add a little bit to our story here for the deformation is we're dealing with a multi-component system. So there's some amorphous zone and there's the crystal zones. A lot of times most of the stretch that we get from creep is in the amorphous zone. So one reason we can use polyethylene is because it has crystals in it. If it wasn't for the crystallinity in polyethylene, it'd be so soft that you couldn't use it as a structural material. This is probably a good starting point when we're going to talk more details about forming. So if we casted the polymer and got these ferrites that we've talked about 2-3 lectures ago, and now we start deforming them, they'll break down and the crystals orient themselves in the direction of pulling. So now all of a sudden you transition from having mostly the amorphous zone inside the spherulite stretching to essentially having all the crystallite lined up to make a cord. So if you have a nylon cord or a polyethylene cord, you're looking at a strength that is about 5 times what you got out of molding, because now everything is well oriented and everything is also more resistant to creep. So you wouldn't use a nylon rod if it was injection molded. It will literally creep on you a lot. But after you've gone through all this drawing process, you get to a point where there's so much hardening, so much orientation that now you are also more resistant to creep. So that's probably the biggest advantage of being able to draw and have ropes that will resist, 1,000-pound capacity for over an extended period of time. So we'll take that topic up and start talking about more details on the injection molding and composites that you can do with the polymers. That would be Thursday. Thank you.